Natural hazards are all around us. Earthquakes, volcanic eruptions, landslides, and tsunamis are all natural processes, but are considered hazards when they have the potential to harm people living in the affected regions and cause billions of dollars of damage. In many cases, these risks are reaching farther and becoming more severe due to climate change. Geophysicists play a vital role in assessing the potential risks from natural hazards, and geophysical research can point to ways to lessen the impacts of these hazardous events. This research involves making observations using a wide range of tools and techniques. For example, you might find a geophysicist excavating a trench to expose rock formations that show signs of past earthquakes. Or maybe you would find geophysicists in their lab using computational techniques like machine learning to resolve patterns in large datasets of seismic activity near volcanoes. Or perhaps you would see them collaborating with other scientists, government officials, or members of community groups as they develop plans for dealing with future hazardous events. In short, geophysicists seek to understand the geologic history of an area, model particular hazards, and help mitigate future disasters. Much as we might feel the ground vibrate as a heavy truck passes, geophysicists are watching for vibrations traveling through Earth's crust from processes like movements on faults. Geophysicists use automated techniques to determine the location, magnitude, and degree of shaking or intensity of the Earth's movement to decipher what happened during an earthquake. These data can be used to send alerts which may be forwarded to communities close by before more damaging earthquakes arrive. While it may only be a few seconds of warning, this time allows people to move to safer locations. Offshore earthquakes may trigger tsunamis due to offsets or displacement of the sea floor. These fast-moving waves can pile up water as they approach the shore, resulting in a destructive impact on coastal areas and shorelines. Geophysicists use sea floor pressure gauges and sea surface buoys to help them model where and when a tsunami may make landfall and how far inland it may travel. These models must forecast potential dangers worldwide because tsunamis also often make landfall very far from their source. For example, a magnitude 9.1 earthquake triggered a tsunami that devastated communities along the coast of Sumatra in 2004, before also traveling around the Indian Ocean and resulting in dozens of deaths along the African coast 5,000 miles away and 8 hours later. Geophysicists monitor volcanic unrest and activity using seismometers, geodesy, and microphones. Around volcanoes, seismic waves are generated by magma breaking rock as it moves through the crust, or at the surface by explosions, the crash of landslides, or volcanic mudflows, called lahars. Magma movement can also cause parts of the surface around the volcano to deform, which can be measured by geodetic instruments such as GPS and tiltmeters. On the surface, they also incorporate microphones that measure low-frequency sound, or infrasound, to detect remote volcanic explosions, gas releases, rockfalls, pyroclastic flows, and lahars. Together, these tools provide information about the volcano's activity, even during times when the volcano is obscured by darkness or poor weather conditions and can't be seen with cameras. Geophysicists are among the members of the Volcano Disaster Assistance Program, or VDAP, that provides expertise and essential monitoring equipment to help reduce the impact of eruptions around the world. VDAP is a vivid example of how geophysicists collaborate with others to make sense and meaning of their data. Understanding natural hazards and their potential impacts on communities is not a one-time task. Hazards and communities change over time. Human-related changes to our planet, such as induced seismic activity from the oil and gas industry, have already resulted in changes to natural hazards and risks compared to even just a decade ago. The impacts of natural hazards ultimately depend more on preparations taken before the event occurs. Ensuring that people are safe from natural hazards requires effort from many partners from a variety of disciplines and backgrounds. Scientists, engineers, and community leaders work together on topics that interface with the public. Physical scientists like geophysicists lend their expertise to interpret data used to generate hazard maps and to predict the expected range of outcomes for risks of different sizes. Engineers consider structural damage caused in the wake of hazardous events to determine whether a building is safe to reoccupy after an evacuation. Social scientists use interview and survey techniques as well as media analysis to assess knowledge about natural hazards in a particular area and understand if past preparation efforts were effective. Community leaders, tribal leaders, and other elected officials pass laws and make guidelines and plans to communicate evacuation information to people. Emergency managers and first responders integrate all these data to generate disaster response plans to help their communities prepare for emergencies. Together, teams of experts help educate and prepare the public for future hazards and risks, sharing information about how people can protect themselves, their homes, and their livelihoods. Given the ever-changing nature of our planet, our growing populations, and a warmer climate, we will continue to face natural hazards that require novel, interdisciplinary approaches. Geophysicists, driven by humanitarian concerns, work to understand the hazards that threaten us, prepare for them, and work with others to minimize risk and prevent disasters in communities all over our future world.